and welcome to the first installment of the damage analysis series here on the June 1st YouTube channel. This is going to be a series where we're going to explore historical tornadoes and get a little more context into the damage they cause by examining forces at play and looking at structures in order to provide a better understanding at just how intense these storms can be. My name is Ethan Moriarty. I'm a mechanical engineer by training, and I have a fascination in tornado damage forensics engineering. With the introductions out of the way, let's get in today's case, the Vilonia Mayflower EF4. First, I would like to get into a little bit of the brief history about this tornado just to put into context what we're dealing with here. The Vilonia EF4 took place on April 27th, 2014. Now, if the date April 27th sounds familiar, this is the famous day from the 2011 super outbreak where there were multiple EF5 tornadoes that broke across the southeastern United States and is regarded as one of the greatest outbreaks in American history. In the context of Vilonia, they were actually impacted by the super outbreak, but not on the April 27th day, but of the first day of the outbreak, of a matter of fact, April 25th, 2011. Vilonia was impacted by an EF2 tornado on this first day of that historic outbreak, and it prompted a lot of residents to get storm shelters installed into their homes after they saw firsthand what could happen in an intense tornado. While it sounds like a good thing that people bought storm shelters for their homes, it unfortunately backfired in a case, and this is one of the main talking points that I want to get into with the Vilonia EF4, but first let's kind of wrap up the history of the tornado itself. This tornado lasted for 1 hour and was on the ground for 41 miles over mostly open country, but yet there were a couple of communities that were heavily impacted, those being Mayflower and Vilonia. There were 16 fatalities with this tornado, which was the deadliest in Arkansas state history since 1968. Not only that, there were also 193 reported injuries as well, so this was a high-impact tornado. The official rating from the National Weather Service and outside engineering experts rated this tornado as an EF4 with estimated peak winds of 190 miles per hour. Now, this is one of the gray areas when it comes into the EF scale. I've covered it in a previous video, my EF scale video, which will be linked down below or in the cards somewhere. We know that the EF scale is not perfect, but I'm trying to at least give you a little bit of context with these damage analysis videos in order to tell you why a decision was made, even though it is likely that this tornado in particular probably exceeded the 200 mile per hour threshold. But when it comes to structures and how they were built, if it can't survive before 200 miles per hour, you can't verify that threshold. So we'll get into that a little bit more in a minute. So if we look here, I have imported the damage survey into Google Earth here, and we'll start off really early in the track actually with one of these first DIs, which is this EF3 over here. And if we change the satellite imagery back to after this tornado, right in here, this is after the cleanup, it seems, but fortunately we have all of the information we need right here. So a couple of notes from this damage indicator rated EF3. This was labeled as a family residence of 1 or 2 floors. The degree of damage: destruction of an engineered or well-constructed residence, swabs swept clean. So keep in mind, some of this terminology that I'm using is explained in my EF scale video. I highly recommend watching that. The estimated peak winds of this DI is 165 miles per hour, so putting it at the top end of the EF3 category. And on first glance, we're looking here and we see anchor bolts. And that's one of the first things that a lot of people look at when we're looking at a damage indicator, is the presence of anchor bolts, and that's like the number one go-to argument for everyone. But anchor bolts aren't everything. If they're not installed correctly, what good is that going to do you? And the big thing in this case of this damage indicator is that there was no hardware that cinched down the sill plates. So the sill plates are the 2x6s that line the walls, particularly on the exterior, but in this case it looks like there were some on the interior walls as well. But we see the anchor bolts that are lining the perimeter of this house, We got anchor bolts in the sill plate, but if you don't have any hardware, washers and nuts locking down the sill plate, that isn't going to do you much good in the up and down direction. The anchor bolts are good in the sense in the, the translational across that, if we were to make a plane across the foundation, the anchor bolts are going to keep you anchored across that flat plane. But if there's any lifting force, and in tornadoes, there's actually quite a bit of lifting force that takes place. The big thing is that there's a big pressure differential that takes place when a tornado moves overhead. The internal pressure of the house is significantly higher than the tornado. Tornadoes are very low pressure. There's also a lot of wind moving over the structure that's going to be generating lift on the structure. So there's going to be a huge pressure imbalance, and ultimately that uplift force, if there's no retention on the sill plates, you're almost going to lift the house right off of those. It's also worth mentioning that if the anchor bolts were secured, the walls probably still wouldn't have survived because there likely wasn't any extra reinforcement on the studs. They were probably just straight nailed. So you have your stud like this, straight nails going into the stud from the bottom, because they build the walls on the ground and raise them. In that case, these houses aren't well designed for that tension case. So a lot of uplift force, tension on the studs, it's not going to be a good scenario. The unfortunate thing that happened at this damage indicator that I want to point out is that there were 3 fatalities that occurred at this location. Early on in the tornado's life cycle, so there probably wasn't too much warning. Though this was a high-risk day from the National Weather Service Storm Prediction Center, it's a case of being weather aware, but until a tornado is bearing down on you and you have minutes, if not seconds, to act, it's a very unfortunate case of, educating the public and communicating weather threats that are likely to happen this day. And based on the image that we have here, granted we don't have, any context around the property, but it doesn't look like there's any sort of storm shelter that they could have taken shelter in, never mind a basement. So with this initial DI, I want to move further up the track over to Vilonia, to the damage indicator that actually was responsible for classifying this tornado as 190 miles per hour. And that's over here at this location. So if we update our satellite imagery, okay, here we go. So here is it's not the best resolution from satellite, obviously, but, clearly we got a house that's been completely slabbed and obliterated, the debris scattered all about. The good thing is that we can go into street view with this house and see what it looked like beforehand. So here is that residence that we saw. We got a bunch of trees around, some hardwood trees. Pretty standard looking house. It looks quite nice. It's unfortunate that it succumbed to the tornado. But let's take a look at the after pictures here in the damage indicator. So some notes from this damage indicator in particular. This was rated 190 miles per hour, so at the upper echelon of the EF4 category. Once again, this is a family residence of 1 to 2 floors, and the same note was used as the last damage indicator we looked at. Destruction of an engineered and or well-constructed residence, slab swept clean. And as we can see, there is mounting hardware on this particular damage indicator, as you can see. So a lot of the sill plates are still remaining. That's what's telling me this. And what probably happened was, as I was mentioning earlier, is that there was no additional support with the studs into the sill plate. They were probably just straight nailed, and that's the case of the majority of homes in the United States, so that's not uncommon. So the uplift scenario is probably what caused this house to succumb to the tornado, though there's another thing that I want to point out, and let's dive into that by going back into street view here for a second. And we notice that there is an attached garage, and with attached garages, that is usually the weak point in a lot of houses when it comes to tornadoes. That door is a weak point for winds to enter the structure. And over here too, it looks like we got a like an overhanging porch type situation here. Another area that is probably a big weak point that probably lifted the roof off the structure. But for this tornado to be rated 190 miles per hour, let's get a context in terms of, you know, some of the forces that are at play on this house. So we're gonna do a quick calculation here just to show what is going on with this structure. So let's quickly just kind of sketch some things out. I took some measurements of this house beforehand. So we're looking down on the house here. It is about 75 feet across, and in this direction here it is about 36 from what I measured on Google Earth. If we took a look at the front of the house, like I said, we got that garage in the front there. And the height, we're just going to approximate here, 2-story house, give or take 10 feet per floor. We'll call that 20 feet. So now we got some geometries associated with the house. We're going to make a couple assumptions here, so I'm going to quickly draw an isometric view, so kind of a 3D view of this house. Okay, so this is our house, and we're going to assume that winds were coming out of the south, so if this was struck by the eastern edge of the tornado, you know, you're rotating counterclockwise. If you're struck by the eastern edge of the tornado, the velocity component is going to be coming directly from the south. And this is a southern facing home, as we saw, so wind coming out of this direction, hitting that front of the house, and it was estimated to be 190 miles per hour, so V is our velocity. One thing we need really quick is our coefficient of drag. So, you know, obviously there's going to be drag, which is the force that's actually acting on the front of that house. So it's pushing that house, and every shape has a coefficient of drag. And based on research that I found, a CD of a typical house is around 1.25. So with all this information, we can use the drag equation, which is the force of drag equals 1/2 the density of air times the velocity of the wind squared, the coefficient of drag in the frontal area of the structure. So we have all of our information here, except for our density of air. We will use standard sea level density of air, which comes out to 0.00237 slugs per cubic foot. Slug is the US unit, or the imperial unit, I should say, for mass, if you didn't know. It's a very funny unit name. So let's plug in our values. With all of that, we get roughly 173,000 pounds of force. So I rounded up, so 3 significant digits. How about that? So that is a lot of force. Just for comparison, if you've ever seen an Airbus A380, which is the largest passenger jet in the world, it has these giant Rolls-Royce engines. The force subjected on the house, assuming that the house was still intact, like with that whole frontal area, it probably, probably broke up a little bit, especially that garage area that I was talking about. So we have our jet engine here, right? It would probably be 2 of these jet engines at max thrust being subjected on this house. That's the amount of force that we're talking about with 190 miles per hour from a tornado. So that is a lot of force to be subjected into a structure. And this goes to show that a tornado of upper EF4, EF5 intensity, a typical family house is not going to survive that kind of strength from a tornado. With that said, that brings in the question of storm shelters, which a lot of houses that were impacted by this tornado had, thanks to what had happened in 2011. Residents saw what the super outbreak did to so many communities, including their own, so they decided to have shelters installed in their homes. Let's go to a damage indicator that had one of those shelters. For that, we're going to go over to the community of Mayflower. So here along the Plantation Drive neighborhood, we got a number of high-level damage indicators here, EF3s, EF4s, along the Arkansas River here in Mayflower. This house over here, EF4. This, if we, update our satellite imagery here, there we go. So clearly, this house sustained a extreme amount of damage. The picture from this damage indicator is not the best. They estimated 170 miles per hour here, but I want to pay attention to over here. You see this over here? This is a concrete storm shelter. I want to pull up a important article from this tornado. This is Tim Marshall's official report on the Vilonia EF4 tornado, and it's full of fantastic information. I pulled a lot of information from this for today's video. I highly recommend reading it. I'll link it down below. But something that was identified with that particular storm shelter was that there was a fatality at that storm shelter. So there were 2 residents of the house in that storm shelter, and one of them was a fatality as a part of this tornado, which is particularly unnerving to me because these residents paid good money probably for this shelter to have installed in their house and assumed that it was going to save their life in the event of the tornado. And the reason as to why this person passed away in the tornado was because of poor construction of this storm shelter, and we're going to dive into that right now. Pulling up on the screen here, we have the actual report, and we're going to scroll down to the storm shelter that we were just looking at. So here we go, moving in here to that storm shelter. So what appears to have happened here is that the door was struck by windborne debris, and something with quite a bit of force, as what ended up happening is that the door frame that this door was a part of succumbed to the forces from the impact and separated the frame at both the lower and upper deadbolts. So there's 3 deadbolts on this door. I'm gonna quickly, we're gonna go to the middle of the canvas here and kind of draw out the storm shelter. So we're just gonna take a quick kind of 3D view of the storm shelter here. Important design things that is going on here is that this is built from, concrete blocks, so, a pretty sturdy type structure, right? So these are filled concrete blocks with rebar and concrete in between the blocks, and then a poured concrete roof with also rebar. And then on the front here is a steel door. Now, the steel door and storm shelters in general are supposed to adhere to what is called a standard. So in engineering, standards are used for a lot of different things. Standards serve as guidelines that, you rate your designs to, and they're very important for all sorts of engineering, particularly for civil engineering and mechanical engineering, obviously. But the ICC 500 standard is specifically for storm shelters. So what's significant about this is that the door used on this storm shelter and a few other storm shelters noted in the survey was that this door was not compliant with the standard. The standard requires the doors to pass a significant impact test. So the builders of the door, they'll take one door that they designed and subject it to this test in order to certify the design, basically. And what it calls for with steel doors that are used for these types of storm shelters is to survive 3 impacts from a 2x4 by 8 foot. Oh, helps if I get my dashes right. A 2x4 by 8 foot piece of wood, a standard 2x4 pine wood, 3 times, moving at 100 miles per hour. So that is a lot for a steel door to handle, because obviously these doors aren't solid steel. That would be an extremely heavy door, as well as the cost of the door would go way up. So engineering a lot of the time is a balance of, meeting your requirements and trying to lessen costs, and obviously things like weight, for example. So you have design constraints, which I don't know if people that aren't engineers realize, is that, you can over engineer like a bridge, for example, but it's going to cost a fortune. So it's a weird thing to say, but if you're designing a bridge, for example, you're going to want that bridge to barely stand in that sense. You want it to meet all your requirements and have certain safety factors, of course, like that's definitely required, but you can't over engineer it, because otherwise it's going to cost a fortune, right? So in the case of ICC 500 and steel doors, what it calls for is these impact tests that it has to survive. So 3 impacts from a 2x4 at 100 miles per hour. Let's put into perspective the amount of energy that's behind something like that. So one of my favorite equations that you've seen a couple of times on the channel here is kinetic energy equaling 1/2 the mass times the velocity squared. To get the mass of our 2x4 here, we need the density of pine wood. If you notice here, the letter that I keep using here is the Greek letter rho. It's commonly used for density. But the density, the average density of pine, I should say, since it's not really a uniform material throughout, it's wood, obviously. It's got a bunch of ununiform fibers, but that's our or our density value. And to get mass, we multiply that by the volume times the density. And I'm not gonna calculate it out, I already did it. So the mass ends up coming out to 0.228 slug per, just slug. Which in the context of gravity is about 7 to 8 pounds roughly, so 7 to 8 pounds pound force. So let's put that into our equation over here, our kinetic energy equation. So we got 1/2 the mass, 228 slug, and the velocity is 100 miles per hour, but like I said before, we gotta account for units here, and that comes out to 147 feet per second squared. So once we calculate this out, this comes out to 2,463 foot-pounds. Not to confuse this with torque, I'm gonna convert this to the metric unit of joules. Just because I think joules is a nicer energy unit than foot-pounds, since foot-pounds is also used for torque in the imperial sense. So what does that mean, though? 3,340 joules. That is quite a bit of energy. To put that in perspective, that is the same amount of energy that is in a 260 Remington bullet, which is a medium caliber type bullet. I'm not the biggest firearms expert by any means, but it's a bullet that's used for small to mid-sized game for hunting. So essentially, you want your door to be borderline bulletproof. Granted, the 2x4, you're getting an impact that's a much larger contact area than the size of a bullet, obviously. Bullets like that, whereas a 2x4 is something like that. So there's more area to dissipate the stress that comes from an impact like that. But let's get into the construction of the door that was a part of this shelter that did not meet this impact standard. So if we look at the report written by Tim Marshall, as we can see, the impact by whatever debris it was deflected the door 6 inches, which is pretty remarkable. But once you realize the door, it's not that hard to believe, just as we just calculated, what the potential velocities are of some of these objects and how much energy they possess. Inside the door, to lighten it up, is a bunch of honeycomb cardboard, which structurally is borderline nothing. If anything, for the door to meet that ICC 500 standard, you're gonna have to have some sort of steel stiffeners in there. I mean, obviously the door can't be solid steel, as for some of the mentions that I talked about earlier, but this is really unfortunate to see that a storm shelter was built with a door that doesn't have the right materials in order to survive what is necessary to survive a tornado. What was identified by Tim Marshall was that the door that failed on the Arkansas shelter had 18 gauge steel, which is about 1.2 millimeters in thickness, when ICC 500 calls for 14 gauge steel, which is about 2 millimeters in thickness. So it doesn't sound like a big difference, but in the context of steel is a metal that likes to deform a bit, and that's a good thing because it kind of absorbs a lot of the energy from the rest of your surrounding structure. The other thing that was noted was the material used for the hinges. The hinges used in this shelter were 11 gauge steel, so around 3 millimeters in thickness, whereas the approved hinges for an ICC 500 standard door would be around a 7 gauge, which is around 5 millimeters. So the weak hardware ultimately, was the main failure point, though the thickness and non-supported interior of the door allowed the door to deform significantly, and then in turn caused the hardware to fail, so the door frame around it supporting it. So the deadbolts, obviously they're made from really strong steel, so they're going to be able to dissipate a lot of energy, but the frame surrounding the door is going to ultimately be your failure point if it's not designed to that standard. So now that we've reviewed the main areas that I wanted to focus on in the context of this tornado, what does that mean for, someone that lives in a tornado prone area of the United States? What lessons can be learned from the Vilonia EF4 tornado? I think the first thing that can be, kind of recalled or learned from this is that home construction varies quite a bit. We saw a lot of, pretty well-built houses, simply just not survive a tornado of this caliber. It probably, if it hit, a significant, very well-engineered structure, something like a hospital or something like that, then maybe we could have verified an EF5 wind speed. But unfortunately, you have to work with the damage that is left behind. It's the most consistent way to rate all tornadoes, right? You're not going to have a radar truck next to every single tornado, right? So damage still remains the most consistent method of rating tornadoes. And of course, there's limitations to that, and we've seen it here with Vilonia. What this means, though, in the context of, someone that is a homeowner in, say Arkansas, Louisiana, Mississippi, Alabama, you shouldn't rely on the construction of your house. And as we've seen here, interior rooms in a very violent tornado are not going to be a safe place to shelter. You're going to need some sort of storm shelter to survive or be underground. And unfortunately, in this region of the United States, there aren't a lot of basements, so a storm shelter is going to be your best bet. And that leads seamlessly into my next point. And if you are going to get a shelter for your home, be sure that you're going with a trusted builder that is using materials and designs that are rated to that ICC 500 standard, as that is the golden document that designs must adhere to in order to survive a tornado like Vilonia. You can be surrounded by, huge concrete walls. We saw that. It looked like a very sturdy structure in the sense that, it had these big concrete blocks. It was all filled. It had rebar. But if it has a weak point like the door, of course every shelter is going to have a door, right? If it has that weak point, that critical weak point that doesn't meet the rest of the design, that's your weak point. And as we saw in this tornado, it led to a fatality. With that said, I hope this was a good education opportunity for you, and maybe you learned a couple of things when it comes to some of the forces that are at play in tornadoes, or maybe you learned a thing or two about home construction and shelter construction. If you have any suggestions or other tornadoes that you might want me to look at, please leave it in the comments below. I love hearing what you guys have to say, and I'm sure there are a number of tornadoes out there that we can look into and really get a better understanding of some of the forces and other kinematics that are at play. With that said, I hope you really enjoyed what you watched today. I like doing educational content like this and putting a little bit more of an engineering twist onto this weather type content. So I really hope that you've got something out of this video today. If you liked it, please consider subscribing as it supports the channel directly. We hope to see you in the next video.